Alright, so in this video we finished our examples on what is a convex set, and we're taking a look really at the three main theorems that we're going to be using here. We can actually title this see if I can get this to go right, three main theorems that will make our algorithm work. We can call it the simplex method. That's the name of it, for the simplex method. And the simplex method is the algorithm that we'll be describing in 4.5 for how to solve a linear program. Okay, so Theorem 1 is really a basic one. It says that a point in the feasible region is an extreme point if and only if it is a basic feasible solution. So in 2 dimensions, we were looking at sets like this for our feasible set, and so these right here, right, would be, I didn't really need that one, I guess. These are the corner points, right, or extreme points, and it turns out that these extreme points are also BFS. Okay, we took a look at the reason why that might be, because these points come in to intersections, right, of a certain number of constraints. However, the question is, there are other intersections too. For example, this one. So this is the intersection of some constraints. Why isn't this one also a basic feasible solution? Or why isn't it an extreme point, you could say? Why isn't it counted in the algorithm? Well, you can kind of see what's going on there, right? While we would find this as part of the set of basic solutions, it wouldn't be feasible, right? So this would not be counted. We don't want to count that one. So let's put a red X through that. So we don't want to count that one. We're only counting these in our algorithm. And so we should only compute extreme points of our feasible set. And it turns out, fortunately, those are exactly the set of basic feasible solutions for our LP in standard form. Good. So the next question has to do with how do you represent these points in the feasible set. And it's kind of interesting because any point in the feasible set, this is Theorem 2 now, this is the representation theorem that we were kind of working really hard with convex sets to get, can be written as the vector d, which is the direction of unboundedness, or 0 if the set is not unbounded, plus a convex combination of the extreme points, or the BFS. Okay, so maybe a quick example, maybe a quick sketch. So, whoops, let me redo that here. So, if our set is bounded, then here are so when I'm writing these, right, you'll notice that our LP is in standard form. So this is just the two-dimensional representation. This is not the full representation though, right? Because our full representation well, it depends on how many slack variables we need and that kind of thing. But this would be we'll just say that this is B1, B2, B3, B4, B5, and B6. And in this case, you can see and we've gotten a sense now for how to do it. If I take any point in this set, right, then I can write it as a convex combination of these corner points. Good. Now, what happens if the set is not bounded? So let me remove some of these here. And let's take a look. I might have one set like that and another one like that. All right, we've looked at a set kind of like this before, right? Oops. Good. And now our B's might actually only be like B1, B2, and B3 here. And so the convex combination of those 3 points is really just this little set in here, right? And so in order to get all of these points, we're going to need to take one of these points and add the direction of unboundedness to it. So you can see by sliding this triangle forward, right, I'm going to be able to get all those points that I might have missed here. So that's what the D is doing. D is allowing you to kind of move your little little piece here forward. I'm kind of waving my arms, but you can't see that. Okay, so in this case, so let's just do an example of how I might write this. So suppose my point was here. Then how would I write this as a convex combination? Well, the first thing I would do is I would project this back, right? Because this is a direction along the negative direction of unboundedness. And so if I direct this back, then I know I could hit it here. I could hit my set here. Or actually I could hit it here too. But I could hit my direction of unboundedness here, and let's call that point E. Right, now E is something like 1 minus gamma times B3 plus gamma times B1, right? And then this is D, so therefore X is equal to your D plus your E, which is a convex combination of your points. Do you see how that works? Good. All right. Of course, I could also write it, you know, if I, like I was saying, I could have projected this all the way back, and now this point is a combination of these two, but actually B1 is just 0, so it's actually okay, you can get the idea. I could have simplified that expression a lot, but that's the idea behind this expression here. Very good. All right, so that again is called the representation theorem. I guess I didn't put that label here. This is the representation theorem. Oops. Representation theorem. And what we're representing is the feasible set for your LP. Very good. All right. Now, by the way, do you happen to remember 2 characterizations of D? I'll let you think about those. One of them is that D must be in the null space. Okay, I'll let you think about that. The next one is actually the fundamental theorem of linear programming. And so the idea of it is that if your linear program has an optimal solution, it has an optimal BFS. So the optimal solution lies at a basic feasible solution. Notice that this is a strong statement here, right? That if it has an optimal solution, then it has an optimal basic feasible solution. Okay, so the solutions we're going to be looking for are solutions lying on the set of the basic feasible solution set. Okay, very good. So this just says, you know, this actually gives us an algorithm almost. You know, at least we understand kind of what we need to do if we're looking at a set like this, right? If I have my B1, my B2, if I know what my set of basic feasible solutions are, and I know that the optimum is along these 5 points, right, then why don't I just evaluate my function at those 5 points, and then I've got my max. And that's kind of what we're going to be doing. We're going to start with one basic feasible solution, and then we're going to step into this polygon one by one using adjacent basic feasible solutions, and we're just going to keep evaluating our linear program, and then we're going to stop when it's the largest. That is basically the algorithm we're using, and that is the simplex method. Okay, so of course that's the simplex method with my hands waving around that you can't see. So the next video will be talking about some of the algebra that we'll be using to do this. Okay, I will see you later.